Since the early days of the telephone, many have considered this the heart of the telephone system, the switching equipment that connects one phone to another. To introduce you to switching fundamentals, we'll first take a quick look at the major functions of a typical switching machine. Then, we'll examine the essential components of an analog electronic switching system. In later programs, we'll show you how an inter-office call is switched and how digital electronic switching systems operate. Through the years, switching systems have gone through many changes, but regardless of how each system operates, all central office switching machines solve the same problem. The problem of how to connect customer lines to each other, either directly or through other switching machines. All switching machines, whether old or new, simple or sophisticated, perform the basic task of connecting and disconnecting lines and trunks. This function is referred to as switched service. With earlier systems, providing switched service could be difficult. For instance, the switching speed was slow and the operator had to manually connect calls. From the manual switchboard, switching evolved into a complicated system of electromechanical switches and relays. But as use of the telephone increased, these systems became very expensive to maintain and expand. Advances in computer technology and microelectronics led to the development of modern switching systems that are efficient to operate and maintain. These modern electronic systems have a high capacity, can be easily expanded, and provide a wide range of user services. There are three types of switching systems. They are electromechanical, such as the crossbar, analog, such as the 1ESS electronic switching system, and digital, such as the DMS 100 and 5ESS electronic switching system. Electromechanical switching machines are currently being phased out of use. Industry plans call for digital switching machines to be installed in every central office in the United States. In order to provide switch service to today's telephone customers, a switching machine performs four major functions. Call processing, which includes all the functions involved in connecting two telephones. Administration, the monitoring and record-keeping of billing and traffic information, as well as data on conditions that affect switched service. Maintenance, the detection and correction of trouble in the system to ensure that the switch operates reliably. And customer services, which include additional features such as call waiting, call hold, and conference calling.
Could you hold on for a second, please? I have another call. Hello? Hi, yes. Thanks for returning my call.
These features expand the switch service available to subscribers. In this program segment, we'll focus on analog electronic switching systems. These systems are called analog because the voice or data signals that pass through them are in analog form. In another segment, we'll discuss digital electronic switching systems. To provide switched service, the analog electronic switching system is comprised of two basic parts, the peripheral equipment and the central processor. The central processor is a computer that provides the intelligence to control the switching operations. The peripheral equipment consists of all switching circuits and devices that establish the physical paths between lines or between lines and trunks. Many components are included in the peripheral equipment of the analog switch. In this segment, we will examine some of the key peripheral components. The peripheral equipment can be divided into three key groups. The distributing frames. They connect lines and trunks to the analog switch. The distributing frames are often considered to be separate from the switching system. The switching network. It is a series of interconnected switch frames that provide switched service to lines and trunks. The service circuits. They are special trunks that perform call processing functions such as generating dial tone and ringing. Other circuits used in the analog switch include trunk circuits, which terminate inter-office trunks, and intra-office junctor circuits, which connect calls within the same office. The switching network consists of three main components that interact to switch lines and trunks. The center of the switching network is the junctor grouping frame, or JGF. Here, the other peripheral components are connected to each other. The line link network is connected to the junctor grouping frame. Customer lines are connected to the line link network. The lines enter the line link network through the main distributing frame. In the line switch frame, or LSF, the lines are monitored and terminated. These lines are then connected to the junctor grouping frame through the line junctor frame, or LJF. Through the junctor grouping frame, the line can then be connected with other peripheral equipment, such as the trunk link network, or TLN. In the trunk link network, interoffice trunks and trunk circuits are connected to the rest of the analog switch. The trunk link network consists of the trunk switch frame, or TSF, which terminates the interoffice trunks, and the trunk junctor frame, or TJF, which connects the trunks to the junctor grouping frame. In an analog switch, there may be several line link networks and trunk link networks. In this segment, we'll show only one of each network. As mentioned before, the actions of the peripheral equipment are controlled by the central processor. The peripheral equipment and the central processor communicate through the peripheral bus system. This series of paths provides two-way communication. The central processor both retrieves information from peripheral units and sends commands for the peripherals to perform. Every line switch frame and trunk switch frame is connected to the peripheral bus system through a unit called a controller. The controller executes changes in the network based on input received from the central processor. The controller consists of solid-state devices and circuits designed to translate the received order. By firing pulses to open or close specific switches, the controller establishes the proper switching path to complete the connection. The peripheral equipment and central processor interact to provide switched service. Let's see what happens when Jay picks up the telephone to make a call. When Jay lifts his handset, a sensing device called a scanner detects that his line state has changed to off hook. This detection takes place in the line switch frame connected to Jay's line. The central processor uses the peripheral bus system to monitor all scanners and controllers. The central processor then receives the change of state information about Jay's line. This information is temporarily stored in the processor's call store. The call store is the temporary memory that stores data relating to calls in progress. In order to interpret this information, the processor consults its program store. It contains the software that controls the switching system. Based on the stored program, the central processor decides the appropriate switching action. In this case, it determines that Jay is requesting service and that dial tone should be sent to Jay's line. To initiate this action, the central processor broadcasts a series of orders across the peripheral bus system to the controllers of every peripheral frame in the system. Along with each order, there is an enabling signal that identifies the specific controller that should interpret the order. In this case, enabling signals are sent to the controllers that are going to establish a path through the switching network. These enabling signals are provided via the Central Pulse Distributor, or CPD. Every controller can be enabled in this manner. The enabled controllers then interpret the orders to initiate the switching action. These orders ultimately establish the talk path. In this case, the system connects Jay's line to the trunk distributing frame and the customer dial pulse receiver, or CDPR. The CDPR provides dial tone and collects the dial digits.
When Jay hears the dial tone, he knows that he can begin dialing. Throughout Jay's call, the central processor and peripheral equipment continue to interact.
In summary, the analog electronic switching system performs centralized call processing. The central processor uses its stored program to both interpret and control the switching actions of the peripheral equipment. This type of switching control is called stored program control. Through stored program control, The peripheral equipment and the central processor perform the many functions of a switching system so that a telephone can receive switched service and communicate with any other telephone. In the public switched telephone network, it is the switching machine that's responsible for call processing, administration, maintenance, and customer services. It's no wonder that the switching machine is called the heart of the telephone system. Now please return to the computer so that you can learn more about analog electronic switching systems.
No anchovies. Just pepperoni. Yeah, thank you. Hi, I'm Anna. I just phoned in an order for the family. A pizza. You know, this whole thing fascinates me. The way this phone can be connected with another phone down the street. It's called call processing. I looked into the whole process. While I'm waiting on my pizza, I think I'll call Zelda over in Smallville. That's about 50 miles from here. We talk once a week just to go over all the latest news. As I'm making the call, let's examine the steps involved in connecting this phone with Zelda's. First, it's important to note that my telephone is connected to a different central office than Zelda's phone. That makes our call an inter-office call. By comparison, my call to Pizza Delight was an intra-office call because both phones are connected to the same central office. The steps involved in processing an intra-office call were discussed in a previous program segment. More steps are required to process an inter-office call than an intra-office call. For my inter-office call to Zelda, the switching systems in both of our central offices are used. Remember, the term switching system refers to the central processor that controls the call processing actions and the peripheral equipment that makes the physical connections. The first stage in processing my call is call origination. It begins when I pick up my handset. As I lift my handset, the switch hook contacts close and complete a circuit to my central office, the uptown office. A scanner in the line switch frame of the peripheral equipment detects and reflects that my line has changed to an off-hook state. The central processor monitors and records the change of state information. You may remember that this monitoring process is called supervision. To store the retrieved information, an originating register is found and seized in the central processor's call store, or temporary memory. The central processor executes instructions from its program store and recognizes that I am requesting service. The central processor then sends a command to the peripheral equipment to send dial tone to my line. When I hear the dial tone, I know I can dial the first digit of Zelda's number. As soon as I dial the first digit, the second phase of call processing begins, digit analysis. The dial tone is disconnected and a dialing connection is established between my line and my uptown office, which is called the originating office. As I dial the rest of Zelda's number, the dual-tone multi-frequencies, or dial pulses of the digits, are received by the customer dial pulse receiver, or CDPR. The CDPR is located in the miscellaneous trunk frame, where the dual-tone multi-frequencies are converted to binary-coded decimal digits, or BCD digits. The processor stores these digits in the originating register. To determine how to route the call, the central processor consults the route index table. The table is located in the program store. The route index table directs a call from a given exchange code to the specific trunk group that will complete the call to its end destination. For instance, Zelda's exchange code is 789. According to the route index table, all 789 calls should be routed to the trunk group 45. If all trunks in the assigned trunk group are busy, my call could be blocked. To prevent call blocking, the call would be directed to a special route index that directs this type of call overflow to other available trunk groups. Most areas of the United States now use the 1+ dialing system for toll calls. With the 1+ system, you must dial a 1 before dialing a number outside your area code. If the switch uses 1+ dialing, the first digit is analyzed to determine whether the requested call is local, toll, or operator assisted. If a 1 is dialed, an inter-exchange carrier could be accessed to process the toll call. If a 0 is dialed, the call is trunked to an operator center, usually at a central location. Here, calls requiring operator assistance, such as credit card calls, are processed. If the first digit is neither a 0 nor a 1, the switching system assumes that the first 3 digits are the exchange code. The route index table is then consulted, as I've just explained. If the first 3 digits are neither an exchange code nor an area code, the switching system sends a message to the caller requesting that he redial.
We're sorry, your call cannot be completed as dialed. Please check the number and dial again, or call your operator to help you.
When digit analysis locates the correct trunk to Zelda's office, the third stage of call processing begins, ringing. An inter-office trunk within trunk group 45 is seized for my call. A path is then reserved in memory for the connection from my line to the inter-office trunk. If all trunks were busy, an all circuits busy announcement would be sent to the caller.
All circuits are busy at this time. Please try again.
In some systems, the caller receives a fast busy tone, indicating that the call cannot be completed. Before the call can be advanced, a path must be reserved from my line to an outgoing trunk, or OGT. That is connected to Zelda's office. A transmitter is connected to this outgoing trunk. The transmitter is usually multi-frequency, or MF. An incoming trunk in Zelda's terminating office is then connected to an MF receiver. The advancement of tones, which is called outpulsing, is then initiated from the originating office. At the terminating office, the received digits are stored in an incoming register. Zelda's office analyzes the received signals to locate the called line. The state of Zelda's line is checked for a busy or idle condition. This information is kept in temporary memory in the terminating office. If the called person was already talking to someone else, the terminating office would send a busy signal to the caller. This would indicate that the caller should hang up. Right now, Zelda's line is free. A path is reserved between the incoming trunk and Zelda's phone. To alert her of my call, a ringing connection is established between her line and a ringing trunk. A ringing trunk is connected to a ringing generator. The ringing connection sends a ringing signal to Zelda's telephone. While Zelda's phone is ringing, the terminating office sends a separate audible ring to my line that lets me know that Zelda's line is ringing. As soon as Zelda picks up her handset, the ringing connection is disconnected and the talking stage of call processing begins. If necessary, a billing register in my office notes the exact time that Zelda answers her phone so that my account can be correctly billed for this call. Then, a talking connection establishes a voice path between the peripheral components of our 2 offices. We can then begin our conversation.
Anna, what's new?
Oh, not much here. What's new with you?
Oh, nothing new. How are the kids?
Oh, pretty much the same. What's going on with your new job?
Oh, nothing much.
Throughout our conversation, the trunk circuits of our offices will continue to perform supervision. The terminating office will monitor Zelda's line via the incoming trunk circuit.
Well, there's nothing else to report.
Yeah, next week looks pretty much the same for me, too.
Can't wait to hear all about it. Goodbye.
Talk to you again next week, just like always. Bye. When we shared our weekly news, I say goodbye, hang up the phone, and the final stage of call processing begins, disconnection, which may be performed by either office, depending on which line hangs up first. When the switching system detects that the state of my line has changed to on hook, it waits for a short period and releases the voice path between Zelda's telephone and mine. The billing register, if necessary, records the time of disconnection. Let's review the 5 major stages of an inter-office switch call. Call origination begins when the phone first goes off hook and includes providing supervision and dial tone. Digit analysis involves receiving the dialed digits and determining the proper route for the call. The ringing stage establishes a path between the originating and terminating offices. A ringing signal is then sent to the called line. The talking stage begins when the called line is answered. A talking connection is established between the 2 telephone lines so that the conversation can take place. Finally, disconnection occurs when one of the lines changes to on hook. The talking path between the 2 lines is then released. By applying these major stages of call processing, a technician can play the role of a private eye to isolate a problem situation on a telephone line. By following a divide and conquer technique, the technician can compare the clues of the problem with each call processing stage until the probable cause of the problem can be isolated to one logical area. For instance, if it is possible to obtain dial tone on a line, then it's an elementary assumption that the first steps of a call origination are being performed correctly. If dial tone is disconnected when the first digit is dialed, you can assume that the problem is not occurring during call origination. Therefore, your investigation can proceed to the next call processing stage, digit analysis. Through this deductive process, a technician or any private eye can use the stages of call processing as a guide with which to isolate a problem situation. Inter-office call processing allows me to talk to my friend as easily as if she were right next door. That pizza delivery is right on time. Well, you'll have to excuse me. Goodbye. Now, please return to the computer so you can learn more about processing an inter-office call.
Digital technology has found a place in almost all areas of our lives. This is especially obvious in telecommunications. Digital technology lets us transmit data at ever-increasing speeds.
In this modern central office, a digital electronic switching system interconnects an incredible number of lines and trunks with speed and efficiency undreamed of when the telephone was invented.
It is estimated that in the not-so-distant future, every telephone line will be switched by a digital electronic switching system. Let's compare the digital electronic switch with the system it is replacing, the analog electronic switch. In a previous program segment, you saw that an analog electronic switching system consists of 2 main parts, the central processor and the peripheral equipment. Program software in the processor interprets and controls the actions performed by the peripheral equipment. By comparison, a digital switch operates as a system of separate components, sometimes called modules or nodes. Each component contains the processor and the peripheral equipment needed to perform specific switching tasks. These components can function both independently and collectively. Analog switching equipment includes electromechanical peripheral equipment that physically connects the lines and trunks even though a digital processor controls the switching operations. Digital switching equipment, however, uses transistors and high-speed microchips. Because the physical connections are made by transistors instead of relays or other electromechanical devices, digital switching is faster and more efficient than analog switching. In an analog electronic switching system, an analog information signal must be converted into a digital signal before it is transmitted over a digital trunk. However, to be processed by another analog switching office, the digital signal must be converted back into an analog signal. Yet another conversion is required before the signal is retransmitted. These multiple conversions increase the risk of signal distortion and noise. Since the 1980s, however, digital switching has been possible at the central office. When it enters the switch, an analog signal on a phone line can now be converted into a digital signal at the originating office. It then remains digital throughout transmission until it reaches the terminating office. Digital lines can be directly switched at the central office. No conversion is necessary. Because the number of conversions is minimal, digital switching provides improved sound quality. Digital switching equipment processes more complex signals at higher operating speeds than analog switching equipment. This results in faster call processing and more customer services. Another advantage of digital electronic switching is that it can directly accommodate the signals of many services, including fax, video, and data communications.
As I've already mentioned, the digital electronic switch is a switching system consisting of several components. You may also hear them referred to as modules or nodes. In this lesson, we'll simply call them components.
There are three main components in a typical digital electronic switching system. The primary component is the switching component, or SC. It terminates lines and trunks and processes calls. A large digital switching system may consist of approximately 200 switching components. Each switching component is connected to the communications component, or CC. It switches voice and signaling information between switching components. A message switch in the communications component serves as the system's message center. The message switch connects the switching components to the main processor. The main processor is called the administrative component, or AC. The administrative component controls the entire switching system. It uses the programs stored in its main memory. Administrative functions include making routing decisions and performing system maintenance. Other administrative functions pertain to individual lines, such as special customer services and billing. These three main components work together to provide digital switched service. However, each switching component is capable of directly connecting its lines and trunks. This flexible system is called distributed processing. Before we discuss distributed processing in detail, let's look at the individual units of each component. The switching component consists of several units. The line card unit, or LCU, interfaces customer lines and the digital system. A customer's 2-wire or 4-wire line is connected to one line card. There is a line card assigned to every customer line connected to the switching component. One switching component can handle approximately 3,500 lines. There are two types of line card units. Digital line card units connect digital lines through a 64 kilobit per second direct channel. Analog line card units connect 4,000 hertz analog lines and convert the analog signal into a 64 kilobits per second digital signal. Other devices in the line card unit enable each line card to supply power and overload protection. During call processing, these devices also perform supervision, ringing, and tone generation. The switching component also contains trunk card units that interface analog or digital interoffice trunks to the switching system. Let's look at how a call is processed through the switch. In this example, Gary's phone is connected to the first line card in switching component 1. He has dialed Bev, whose phone is connected to the fourth line card in switching component 3. Since this call passes between switching components, the call request is passed to the administrative component. The administrative component determines which units are needed to route the call and provides the necessary information to these units. In switching component 1, the units that are involved in processing the call include the multiplexer or MUX located in Gary's line card unit and the time slot interchange or TSI. In the communications component, a unit called the time multiplexed switch or TMS is involved. Also used are the TSI and multiplexer attached to Bev's line card in switching component 3. Let's trace the digital signal as it leaves Gary's line card. As you saw in previous lessons, digital signals consist of a stream of time slots. Each time slot may or may not contain a pulse depending upon whether it represents a binary 1 or 0. Gary's line card and a number of others share a common multiplexer. As the multiplexer receives a line card's digital signal, it is grouped into 8-bit signal blocks. Sometimes these groups of bits are called time slots. To avoid confusion, we'll refer to them as blocks. The multiplexer combines or interleaves the signal blocks from its line cards into one bit stream. This bit stream is transmitted to the time slot interchange. This bit stream or multiplex channel is divided into frames. A frame contains one block from each of the line cards the multiplexer serves. For example, if the multiplexer handles 24 line cards, the first 8 bits of the frame are reserved for line card 1's block. The next 8 bits are for line card 2, and so forth. After the 24th block, a new frame begins. The signal from Gary's phone always occupies block position 1 in the frame. When Gary's phone isn't in use, block position 1 is set to be idle. To understand the rest of the process, we must jump ahead and look at the function of the time multiplexed switch. The time multiplexed switch accepts multiplexed channels from the TSIs in the switching components. It then switches blocks onto multiplexed channels going to TSIs in other switching components. However, the TMS cannot reorder the blocks. For example, when a block enters the TMS in the third position of a frame, it must be switched to the third position of a frame that is leaving the TMS. In order to transmit the signal from Gary's TSI to Bev's TSI, the administrative component must identify a block position that is idle on both the channel from Gary's TSI to the TMS and the channel from the TMS to Bev's TSI. In this case, position 3 is idle on both channels. Then, the administrative component instructs Gary's TSI to move his blocks from position 1 to position 3 on the channel leading to the TMS. At the TMS, the administrative component instructs the block 3 be switched to the channel going to Bev's TSI. Remember, Gary's signal is in block 3 of that channel. At Bev's TSI, the administrative component instructs that the signal in the block 3 position be switched to the block position reserved for Bev's phone, which is block position number 4. The signal then moves to Bev's multiplexer, where Gary's blocks are demultiplexed. In other words, they are reassembled into a continuous bit stream. At Bev's line card, the signal is converted from digital to analog and transmitted to Bev's phone. Bev can now hear Gary's voice over her line. A separate path is set up for the signal going in the opposite direction so that both Gary and Bev can communicate at the same time. If a call is processed between lines connected to the same switching component, its time slot interchange can route and switch the call without instructions from the administrative component. After completing any call, the time slot interchange sends the administrative component a message with information about the lines, routes, and length of the call. Along with the time multiplexed switch, the communications component contains a message switch. The message switch receives all messages from the switching and administrative components and routes them to the intended receiver. Without the message switch, the other components cannot communicate with each other. Another important unit contained in the communications component is the network clock. It synchronizes the system with the entire telephone network. The administrative component consists of the main processor and a database that stores and records information for the entire switching system. Through additional data links, the administrative component interfaces with a control center located in the office and with centralized switch monitoring facilities. In this way, trouble conditions or maintenance data can be quickly assessed by personnel in various locations.
The three main components of the digital electronic switch function together according to a flexible system called distributed processing.
In this distributed processing scheme, the switching components perform about 95% of the switching operations between the system's lines and trunks. This frees the communications and administrative components to concentrate on system-wide functions. With the distributed processing, a switching component can operate from a remote location. This remote switching component serves newly installed lines in an outlying area served by the central office. Calls between these lines can be switched directly by the remote switching component. The remote site is connected to the rest of the system through a host switching component located in the central office. Through this connection, information from the remote site is transferred to the communications and administrative components. If a remote line requests a call to another switching component, the call is first sent to the host switching component. The call is then transferred to the communications component, which switches the call to the appropriate switching component. In larger cities, some remote switching components use fiber optic links to bypass the host component and connect directly to the communications component. These optical remote sites expand the capacity of the switching system while providing the increased capacity of fiber optics. With its flexible structure, distributed processing allows for future growth and improved digital services at lower costs.
While we focused on digital switching in the central office, there was also the digital toll electronic switch designed for the toll environment.
In today's toll environment, each inter-exchange carrier, or IXC, operates its own digital toll offices and transmission facilities. Occasionally, IXCs share a toll facility. The digital toll electronic switch includes the same main components as the digital systems used in central offices. However, the primary function of a digital toll switch is to connect incoming and outgoing trunks either from another toll office or a central office. Therefore, the digital toll switch isn't equipped for many of the functions relating to customer lines, such as ringing and dial tone generation and other customer line signaling. The digital toll electronic switch performs call processing functions between inter-office trunks. For instance, trunk scanners monitor the availability of trunks connected to the toll office. If no trunks are available, the digital toll switch sends an all circuits busy message to the originating office, which transfers the message to the customer's line. This is the only status indicator generated by the digital toll switch. Administrative functions of the digital toll electronic switch include selecting primary and alternate trunk routes between toll offices. The switch makes these routing decisions by using its stored program. The database of the digital toll switch records the toll call information necessary for customer billing. Inter-office trunk signaling between digital toll systems may be performed by in-band methods such as per-trunk signaling, which sends the voice and signaling information over the same trunk circuit. Over time, more and more digital toll electronic switches are being equipped with switching points that connect the office with the Common Channel Signaling System 7 or CCS 7. CCS 7 transmits signaling information over a high-speed channel that is separate from the trunk circuits. This signaling system is faster and more reliable than per-trunk methods. Work is currently underway to enable all digital electronic switching offices to communicate by common channel signaling in both the local and toll networks.
Digital technology enables the local and toll networks to provide expanded and improved services. And as digital electronic switching systems continue to develop, the future will offer even faster and more efficient telecommunications.
Now please return to the computer so you can learn more about digital electronic switching systems.